Hello, welcome to one more lecture on our fundamentals and biomedical application of quantum science and engineering. Today, we're going to continue the last lecture where we were able to show to you an equation. And let me explain that I did not deduce the equation. I induced it. I took the properties I know and I say, well, must be that way. And that's the way that Schroedinger did. And that's why this equation is called the Schroedinger Equation. And it tells us, it says that if I have a physical system that's either time dependent or time independent, this must be the equation that gives to us the wave function. And from the wave function, we are able to extract from there all the properties, all the physical properties that we want. It turns out, however, that in some systems, and if the physical system exists in nature, this equation must have solution. So I must have a wave that accommodates there everywhere, right? If doesn't, means that the system is not there, right? So this is a very powerful tool. And this is the Schroedinger equation that we're going to use from now on. And we're going to deal with mostly with what we call a time-independent system. Means that the potential does not depend on time. So it's not like a generic position and time potential, like something that's shaking in time or anything. It's just spatial. Stationary. Okay, in this case, we can show to you that actually the energy of the system is constant, of course. If the potential is not time independent, the energy is constant. And this equation can be reduced to a very interesting equation, a very nice equation, which is the called time independent equation. Basically, this becomes the energy of the system. And therefore, we have that the momentum squared times the function plus the potential energy times the function. The potential, right, times the function, potential energy, is equal to the energy of the system. Okay, so this everything is consistent with what we started from the very beginning. So this is called time independent Schroedinger equation. And it's true for many of the things that do not vary in time. So it will be true for the atoms, it will be true for molecules, it will be true for many things that does not change in time. Will not be true for like when light interacts with the atom, because when light interacts with the atom, the interaction is time dependent. So V will be the time variation of the fields of the light. So then we're going to have to go back to this equation. But for most of the stationary situations, this is the equation that we're going to deal with. And how is this equation? Right? How is this equation? Well, it's easy. How we show that actually when we have time independent potential, how comes that that's the result of the equation? Well, this part is the energy. If there is no time anywhere here, we can separate the variables. This is a very famous technique for solving equations. And just for you to understand, I will give you a few steps. Because, you see, this equation is so powerful because now when we have a physical system, whatever are the energies, this is like a parameter, whatever are the values of this energy that allow me to have solution are the possible energies of the system. So this will be the principle of the quantization of the energy. Is I have a wave, I'm going to accommodate in the physical system, like this physical system, and whatever are the values of this energy. Whatever are the values of those energies that really allow solution for this equation are the ones that represents the possible energies of the system and possible waves of the system and possible properties of the system, as we're going to see. So this equation is, the solution of this equation is basically what's guaranteed to us the existence of the energies and the system in some configurations, which are the configurations that it can exist. If it is an atom, we're going to see that not all energies are possible, only a few, because the wave now accommodates in the structure in a way that let the solution exist. It's not any wave that accommodates anywhere. If you try to put any wave anywhere, it does not work. We know that the system of pool decays, attenuates. We must have the wave appropriate for the system. And that's the main basic of the quantum mechanics. Is once we have this wave equation, the solution will give us the waves that are possible to exist in that physical system. And to do that, there is a compromise between values of energy. It's not energy, any energy. You know, the energy which represents back there, the frequency of the system, cannot be any. It must be discrete. It must be a few energies that really allow the system to exist. And that's the essence of the quantum mechanics. At the end of the day, the energy is quantized. Only a few waves can be representing the system, and then we have what we have in nature. Only a few atomic orbitals, only a few structures, only a few everything, because now this is the equation, and we're going to learn that whatever it exists, the solution is what the nature gives to us. Why? Well, I mean, again, we are great users of quantum mechanics, but we don't know why nature chooses that way to be. It chose, and we learned that, and then we still remain to understand why it's not different. But okay, so for me to explain this for you, I want to, as I told you, if this equation, the potential is the way I wrote here, is time independent. So I have everything with x in one side and everything with t in the other. And that's a good indication that I can separate the variables. And that's what we do. To explain what's going to happen, I'm going to call the overall wave function as a spatial part and a time part. Phi of t is the time part, psi of x is the spatial part. And I call this capital psi. And capital psi must be the solution of the overall equation. And if I put that in the equation, what I get is that minus I ddt of this is equal to the spatial part with only axing this guy, right? Maybe I should do that. What we're going to do here is take this, and then we put in minus I h bar d dt of psi capital. This is equal to minus h bar square divided by 2m. Second derivative with respect to x of psi capital plus v of x psi capital. And then now we put this phi times psi of x on the solution. Capital psi is the total wave function. In this side, we're going to have this. On the other side, we're going to have the x part acting. But we know that this part is the energy, so we can write the energy here. And we know that since the potential is not time dependent, the energy must be constant. If the energy must be constant, then I have this. And of course, in one side, which is the spatial part, I have this equal to E, right? Well, I have all this. But then when I substitute, I'm going to have two equations. One for phi, which is the time independent, and then the x dependent disappear. And one for the x dependence, which is basically this equation. And both must be equal to E. But since they are separable variables, we separate them. So it's like this is equal to E, this is equal to E. So the spatial part is equal to E, and the time part is equal to E. This is what I have done here. And in the case of the potential being independent of time, the solution of this is trivial. What is the function that I take the derivative and I repeat the function? It's the exponential. Therefore, if the potential is time independent, the solution is just a normal sinus-cosine variation with time. It's a simple oscillatory solution in time, and the energy is constant. Whatever are the energies that are allowed, as I've told you from the beginning of the use of the equation, you must have different variations here. So that's why, you know, I just make an addition here to show to you that this part is obtained, the time-independent equation is obtained when the time variation is not present in the potential. Therefore, we can separate the time from the space. And what we get is something that we knew before, that energy of the system is an expression of its time evolution in time. Right? It is an expression of the wave function time evolution in time. All this I think is redundant. The energy is a characterization of the time dependence of the wave function. This is the better statement to make. Right? And we now have this wonderful equation that I want to put back here. So we have the overall general equation, which is with time variation, everything. And then in the case of non-time variation of the potential, we end with this equation. This is the equation that actually is a generalization what de Broglie and Sommerfeld and so on to obtain the wave function of your system. Okay, so besides this time oscillation, this time variation, which represents simple oscillations in time, we must have in mind the actually equation, right? And we have now an equation that's supposed to give us the wave function of any physical system. And we can apply for many things. You know, it's unbelievable what this wave equation is able to predict. We know that molecules, for instance, they have structure. Those structures which are dependent on the electronic orbitals of the atoms, right? We learned that even in high school when we make the chemical bonds and everything. That is in this equation. It's unbelievable, right? Of course, we obtain an equation which I only put x dependence. And if I have a y and z dependence, well, it is very nice that p squared is actually px squared plus py squared plus pz squared. If my momentum has many components, they compose in quadrature, as we know. We learned that. The modulus of the momentum of the particle square is the sum of the square of the components. And it turns out that derivatives are also additive. So here I'm going to have a variation with x, a variation with y, a variation with z for each of those components. We all know that when I have this, I have what I call the Laplacian. The Laplacian is a mathematical operation which is the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z, right? And this will be equal to, of course, the potential also may have x, y, and z dependence, and everything else stays the same. I just have more variables that gets into the wave equation. because when we're going to solve for the orbitals and everything of the atoms and the molecules, we must somehow know that we have to go to three-dimensional, right? So this is something that we cannot avoid, right? But this is fantastic, because the time, the energy of the system just give you a simple variation when the potential is independent of the time, which is the case of the nuclei holding an electron, or many of the situations that we have. In some cases, we do have time dependence. And we're going to see some examples of this. But before applying this equation for situations that we want to know what's the behavior, I have to fulfill a promise that I did. And my promise was, I have to explain to you wave of what? We build up an equation. We got the de Broglie hypothesis. We understand a little bit the Sommerfeld quantization, but we don't know what this wave is made of. So I get to start to answer what is this wave is made of, so you can have an intuition for everything. You already agree with me that most of the properties of the system can be extracted from this wave function, right? So it is a good thing to have on hands, and not only the energy, but this is also a good thing to have. But I must now get serious and try to explain, is wave of what? What is wave we're dealing with? Because we have no doubt, or we have convincing evidences of the wave description for the physical system. We only do not know what's this wave. Is wave of what? Wave of mass? Wave of matter? What wave? Because, every time we have wave, the wave is wave of some physical properties. So we have waves of sound, which is made of pressure waves. The pressure of the gas increase, decrease, and this propagates. So when I speak, I produce kind of waves of pressure. Increasing pressure, compress the air, decompress, and keep going. So in this case, we could say that waves of pressure. We could say also that the sound propagating because it's pressure, and pressure is connected to density in the gas or in many materials. We could be also wave of density. And we have specific equations for determining those waves. And normally when we determine these waves, the conditions will give us special characteristics like the speed of the sound and everything. If we have light, we know the light is made of waves of electromagnetic field. So we have E and B oscillating time in any space, propagating. So we know what the wave of light is made of. That was a tremendous big contribution to science, right? Understand that light was made of waves of electricity and magnetism. If you go and look to your swimming pool and see the waves of water, we know what those waves are made of. If you look at the waves of water, they are made of up and down, right? It's gravity and coming down, gravity and coming down of water mass. It comes up and down, and then when it comes up, and then when well down, pushes the other part up, and so on, and this waves propagates. Or when you have a string or a spring also is elastic waves propagating by compression and decompression. So we know that's displacement waves. So any wave is made of something, right? Any wave is wave of something, and we must know now the de Broglie waves are waves of what? right? We know that whatever exists the wave, the particle is there, right? Because we are dealing with a particle of mass m. We even came with an expression for the equation. I'm taking the time independent or time independent, doesn't matter. Two equations are here. But if we look into this, we know that we have a particle with mass, and this is a value of the mass. And then we have this wave, and we have to make an interpretation where is this wave of, is the mass that's distributed in space. That's really hard, because when we have a free particle propagating in space, you know, it's occupied everywhere. The mass is spread everywhere. It's kind of hard, right? The momentum must be also spread everywhere and so on. So we still needed to now build up this concept. What is this wave made of? Okay, so we must first collect a few properties of this wave. And then we can see if we can come with an explanation. What is this wave made of? Matter waves, de Broglie waves, what are they made of? Well, one thing is that whatever the wave exists, we may find this physical particle there. So whatever the wave exists, we can find the matter, we can find the electron, we can find the particle, we can find it, everything. So it must be where the particle has some chance to be, right? Pay attention to those words. The particle will be whatever has a chance to be. Now, the equation do not, we have an equation, and I can guarantee you in advance that that's good equation. You know, this equation build up on the constants of energy, momentum, potential. You know, this is great. It's an equation that is what we work with. This is the master equation that will explain us the world. And then there are some evolutions of this equation, but that doesn't matter at the moment. Or the equations do not provide information about the nature of the wave. The equation does not tell us exactly what is the wave made of, right? Because we constructed this wave function based on the fact that it must be a wave, because we observe many phenomena that's like a wave. But we did not, we could not come with a wave of what based on the equations. The equation will help us to solve many problems, but will not tell us the nature of the wave. To tell us the nature of the wave, we must come with some interpretation. And there was a very nice scientist, nice physicist, Max Born. Max Born, he was the first one to provide an interpretation for this wave of matter, this wave that we get from the Schroedinger equation, this wave that explains the diffraction, that explains the interference, that explains the nature of the atom, that explains everything. He was the first one to do that. And I'm going to try to explain to you how Max Born came with those concepts. Okay? So, first of all, you see that the quantum mechanics somehow was born observing the light waves and the behavior of the photons. You know, the black body radiation, the Planck's law, help us to construct the concept of the wave mechanics or the quantum mechanics. So what Max Born did was this. He used this concept. He went back and said, look, if I look to the light, there is this particle wave duality, which means that, you know, when I detect, is like a particle. But when I don't detect, when I see this evolving It's like the wave. And then he tried to extract from there, exactly like the Broglie. You know, I think we're not so wrong if we say that the light was the motivation. The light was the motivation for the beginning of the quantum mechanics, right? So what Max Born did was, okay, let's observe the light, right? Learn with the light, and let's try to make sense of this matter wave. And then he used this interpretation of duality wave particles. Because actually we have a particle. We have a mass. We can even weight this mass. And if we look to the electromagnetic phenomena, you know, the electrical field, for instance, is oscillating like this, and then the intensity is like this amplitude square. In fact, to tell you the intensity of the best will be the amplitude here. So the amplitude of the electromagnetic field square is the intensity of the light. It's proportional to the intensity. It gives us the intensity. Actually, if you already learn electromagnetism, you know that we create the concept of the Poynting vector, that is the flux of energy and everything. But when we do the experiment, we know that the light, if we assume that the light is made of particles, and we do the experiment like this. Oh, by the way, and whatever I have more intensity, I have a bigger chance to find the photon. So actually, the intensity is the energy per square centimeter per second, right? And if I divide by h bar nu, I have the number of photons because the energy of each photon. So I can express intensity as photons per second per unit of area that I am illuminating and so on. So whatever the intensity is high, I have more photons. And when I do the experiment of the interference, double slit, you know, we send light here. Let's now assume that the light is made of photons, right? Those packages, those particles of light. And to really obtain the structure of the interference, if I look far, if I look to some distance, and I look at the profile of the intensity, what I get that the light passing through those slits, they will make this very nice pattern that I see a central pattern with more intensity, and then I see the shoulders, the secondary, and so on. And this is the intensity, right? This is the brightness. I see this, and this is whatever the light is or not. If I look here, and I'm considering photons, I see here more photons, right? More photons here than here, because the amplitude square here, because this is the intensity, and the intensity is the amplitude square. So this is whatever I see more photon. People has done such experiment. People has done the experiment of the interference, send the photons by photon. So if this is a very tiny light, a very dim light, very, photon by photon, boom, boom, coming here, of course, the photon will be detected either here or here, because when I detect one photon. I cannot detect half here, half here. So when they do this experiment, they keep accumulating how many photons they count. And they keep accumulating the counting. And then they see that here, more photons come here than here, and so on. And if they relate that with the amplitude, they see that actually it's very proportional. Whatever I have more amplitude of the wave, I get more photons counted. In the beginning, but I have to accumulate in time this, right? At the beginning, I have one photon here. So if I do photon counting of this, what I'm going to get is, I get one photon here, another here, another here, oh, and then one here, and then another here, another here, another here, and then one here, and then another here, another here, another there, and then another there, another here, another here, another here, and then another there. At the end of the day, I see that I have much more photons here, and then here. And that's proportional to the intensity. And the intensity is the amplitude square. So, the interpretation for this electromagnetic part is that the amplitude square is actually the probability of finding more photons. It's the probability to finding the photon, in fact. This part doesn't need it. Larger amplitude, larger probability to find the photon. And then when I accumulate everything, I build up this wonderful interference pattern or diffraction pattern from the double slit. This is what I get. And then Born look into this and say, well, it's so similar, the wave of the electromagnetic wave with the photon and the principles of quantum mechanics, that I think the wave we are getting is just the probability to get the particle. You know, in the case of light, it's the photon, the particle. But in the case of my particle, it's my particle, any particle. So then, Born came with what we call the interpretation that we use even today, that based on the duality of the wave particle and with light, right? He starts with light. He looks to light. He looks to the phenomenon of light, which is a wave particle type of behavior. And then he extended the interpretation to matter waves. He extended the interpretation to matter waves, to psi. And then the statement that we're going to say, I hope that was more or less the words of Born, is that the probability to experimentally find the particle in a region of space at certain time is proportional to psi square. That's the interpretation. So he's giving to us a probabilistic interpretation for the wave function. Therefore, even though the wave function carries a lot of physical properties, but the wave itself is not like in the light, that the wave is the electrical field or the magnetic field, or in the sound that the amplitude of the wave is actually the pressure. Here the wave function is not a physical property. It's just a quantity that contains the physical property. Well, you know what we are getting, right? We are getting to the interpretation that we are dealing with a wave of probability. The particle is there, but probabilistically it is distributed. And because all the property of the system is contribution of all the probability to where it can be, it turns out that it's like the particle is distributed. When we see the wave function of particle in a box that's zero at the walls and build ups and comes down, that square is actually the probability. If I come with a gun and give a shot, I'm going to hit the particle with frequency that's dependent on the amplitude of the wave function. So, thanks to Born, we have a probabilistic interpretation for the quantum mechanics, for the amplitude of this wave. So actually this is then a wave of probability. It's a wave that square gives us a probability distribution. So whatever has oscillations in space is because the probability is oscillating in space. Whatever has oscillation in time is because the probability is oscillating in time. And this phrase that I add here, that the psi, or the wave function, is not a physical quantity, but it contains all physical information, right? Psi square now comes, right? The final statement, psi square. This is a physical quantity because it's what they call the probability density. Remember when I started the course, I explained to you what was probability and what was continuous distribution of probability. Continuous distribution of probability is characterized by a distribution, a function, distribution function of probability. And this distribution function of probability tells us how is the probability distribute with some parameter. Here, space and time. It makes sense? Well, the diffraction experiments, the wave in the atom, the particles mostly the diffraction of the electron in the atom, and many other experiments, it makes sense to have this interpretation. I know it's hard to get to, but once you get through, it comes to your intuition, and then you make sense of everything. Nature is like this. I know that you're gonna question, and you always want, this is a mistake, you always want to come with some classical interpretation for the quantum mechanics. No possible. The quantum mechanics cannot be explained by classical mechanics, otherwise we just need the classical mechanics. So we have to start to put in your minds that this is an interpretation. Of course, we're gonna show that this makes sense, and we have a lot of situation where this is important. Basically, this is the density, because the wave function square has the dimension of inverse volume or inverse space or whatever, if I'm dealing in 1 dimension or 3 dimension. So the wave function square actually has dimension of 1 over space. And multiply by space give us the full probability. So the probability, if I have a wave function and I ask what is the probability to find, so I have a wave function here, I don't know, it's a function, right? So I have a function here. If I take a little space between x and x plus dx, the amplitude square times dx is the probability to find the particle between x and x plus dx. Right? That's a very important interpretation. I was going to highlight this, because that's the real thing we have to know. This is probability density. So that's shocking for some people, but is reality, or at least at the present is our reality. The wave function square has meaning, density, probability. That's why the quantum mechanics works with average values, work with probabilities, because when we get the wave function, we're going to be able to at most determine probability distribution of things, right? Probability distribution of things. But once you detect the particle, it's a particle, you detect, boom, an electron pass. But if I look in a space, I'm going to see that it detects here more frequently, there less frequently, so I build up the wave function square based on that, if I want. This is the wave function. Is a wave of probabilities. The wave function square represents the density of probability. Large values of psi square means large chances the particle be there. you have to understand that this doesn't mean that I'm fractionating the particle, putting a little piece of it everywhere. No, it's the single particle is there, but it's probabilistically distributed. And this probability determines the property of everything. So when you see the orbital, it's because that's where the particle is in space distributed. The particle is distributed in space everywhere there, because probabilistics can be everywhere with some value. Therefore, all the properties of the system relies on that. So finally, for this lecture, if I had to answer what is this wave made of, we have to highlight that's a probability in space-time. And from that probability in space-time, we should be able to extract all the properties of the system. Let me only stress to you that does not mean that the particle is fragmented and distributed. It's not a little piece of electron everywhere. No. It's the whole thing there all the time in all space. And there is a big difference between probability distribution for an event. I have to highlight this also in a very good color. You have to understand that there is a big difference between a probability distribution for an event and the event itself. So when I do the diffraction double slit experiment for electrons, you know, the electrons scattering passing in each slit, that's the event. Now, the probability that will pass in each slit give us the distribution that will turn out to be the diffraction pattern in some distance. Right? So, there is a big difference between the probability distribution for an event and the event itself. For example, for Bragg, before we measure Bragg scattering of electrons from a surface of a crystal, before we measure, we have a wave. After we measure, we get the particle. Always we detect the electron, it is one electron, it's a particle. But when it's in the physical system, it's a wave, it's a distribution. And the properties of the physical system is given by that distribution. Sorry, nothing I can do about. Right? So this is important, and that's a concept. I know it's hard, but once you swallow down, it makes everything easy. I know it's you know, quantum mechanics is a easy concept. You see, it was built in principles that are evidences and are correlations and things like this, but sometimes it's hard for us to accept because we insist with the fact that we want to explain quantum mechanics with classical mechanics, and that's not possible. We cannot do that. Well, today we explain what this wave is made of. I still want to build up a few more properties of this wave function, so you understand everything else we're going to do. The last lecture we learned the equation. Today we learn the interpretation of this wave. And next lecture we're going to start some applications. But before start the applications, we have to learn how to apply the wave function. Once we get a physical system and we are able to solve the problem, get the wave function, how we extract from there all the physical properties we want to extract. And that's what I'm going to do in the next lecture. See you then. Bye-bye.